This presentation will serve as an exclamation point to Jack's and to Jim's, and you've just seen the real speaker, not his amanuensis, who I'm just the reporter here. But next slide, please. Okay, this view from the science back room is one that has been conveyed to multiple shuttle and space station astronaut field groups and conveyed at Apollo legacy sites. Part of the field training that astronaut candidates receive involves going to places like the Rio Grande Gorge and observing what the Apollo 15 crew was trained on in preparation for being at Hadley Rill. Okay, the simulations that were conducted for A15, well, for all the J missions, Malberger was adamant, as was Swan and everyone, that the crew, that Capcom and the backroom scientists trained together in the field. Next, please. Okay, the purpose of that was to, and the emphasis on communication has come up several times. This is to evolve a common exploration vocabulary. You don't want to waste time on the ground at Plum Crater defining terms and getting into semantic quibblings. Another purpose was to converge on the best possible techniques and tools to address the science objectives. Now, this is something that feeds directly forward to Artemis preparation. And we, in the course of these field training sessions in the Rio Grande Gorge and around, we initiated a geophysical simulation. And this was at a time when the NASA emphasis was on white-suited astronauts on the red planet. So this was an opportunity to test the J mission strategy in preparation for eventual trip to Mars. As far as what goes into a rigorous simulation, intuitively, it would have to be driven by mission science objectives and conducted at high fidelity analog sites. If possible, which the flight designed and flight tested instruments had been tested on Earth, thinking specifically of the Warden gravimeter and that sort of thing that were used on Apollo 16 and 17. But one of the most critical things to simulate pre-mission is real-time data transmission to the back room scientists. This includes geophysical data, whether it be seismic data or gravity data, and things like spectrometric data, and we'll get to that in a little bit. But the other thing that has evolved since Apollo days is satellite navigation systems capabilities. And for precise sample coordinates and geophysical station coordinates, this is absolutely essential. But emphasis for the Artemis simulations should also include the data transmission. Next, please. Okay. The returns on that J mission strategy were many. And these two videos, one for Apollo 16, one for 17, the complete link that you see here is in the abstract so that you can go directly to them. Okay. These are only two examples of the effectiveness of the kind of back and forth that men just show and the crew on the ground. The recorded dialogue, and these are recorded from the missions, in the case of Apollo 16, captures the science return, not just the recognition of the sample, the collecting of it, but a material change in interpretation of the geology at the site. That integrated training gave Duke the background to pick up the sample, provide a description in the moment on the site, and it was clear that the breccia, represented by Big Muley, this 20-pound sample, was different from Highlands volcanic plains material that had been part of the pre-flight interpretation. The recording also includes Duke's admonition that if he fell into Plum Crater while collecting that big rock, Mulberger had it. Okay. Now, as for the Apollo 17 video, Jack's discussion of the moment and the communication requirement there is an excellent feeling for the balance among crew on the ground, the science back room, and in this case, Capcom was involved too directly because, yes, this was the excitement of the discovery. The sampling was very careful, deliberate. The immediate description was disciplined and involved some backing and forthing in the back room about volcanics, were they pyroclastics? So there was an ongoing dialogue while Jack was doing the sampling and description. There was so much enthusiasm and the desire to see and understand more. Capcom did have to enter into this discussion reminding of the oxygen and water limitations for the crew and the insistence to wrap it up and be aware of the time. Okay, next, please. Next slide, please. So the the J mission strategy is directly applicable for Artemis. And in this case, an integrated exploration sim would include data acquisition, communications, data transmission, and interpretation. You know, in the laser altimetry image to the left, see, that is a head-on view to South Pole Aitken Basin. 5 of the 7 National Research Council geological concepts are testable at Schrödinger Basin. The bright yellow S in the southwest quadrant of that polar view is Schrödinger Basin. The of those,
We'll need to move on pretty soon, Pat.
okay, I'm wrapping it.
Thanks.
The two objectives to focus on here are thickness, density, and composition of regolith and of the pyroclastics noted in the right-hand image. Seismic traverses give the maximum resolution for not only thickness but internal structure of such deposits. Okay, other techniques would be Raman spectrometry for the pyroclastics, for chemistry, and core drilling. Okay, next, please. This has come up in several presentations, and this is just a confirming note to say that flexibility, adaptability is prime. Flexibility in response to discoveries like the red soil at Taurus Littrow, and innovation as to repair of the rover fender on Apollo 17 when the fender broke. So Capcom and science team do monitor the time, oxygen, and water limitations, and still optimize scientific discovery. What did not work was overly rigidly scripted EVA timelines. What if we find water ice sequestered in the regolith at Schrödinger? How do we adapt and sample for that? Okay, next, please.
And Pat, if we could wrap up.
Yeah, this is the last one.
Great, thank you.
Next, please. No, it's over. This is for the questions addressed and the summary. That's it.